Okay, I think we're all set in terms of the stream being on, and I don't know if okay. Let me just make sure that I'm in presentation mode and that annotations are enabled. And yeah, once again, I'm sorry if I sound weirder than usual. Still trying to get back to normal with the voice. Okay, all right. So don't know if yeah, maybe we get started with the story for miniature number 22, which asks in how many ways can a man tile a board? And it turns out that the answer lies somewhat in determinants, as we will see in a minute. So, okay, before that, let me just maybe describe the tiling problem. This is okay, so this is a polypad embed. What is underneath here is a chessboard. So you've been given these domino pieces. These are 2x1 pieces, and what these pieces are covering is a 8x8 board. And this is embedded right here. You can go and play with it if you want to experiment with other ways that you can tile the board. You can imagine that there are many ways of doing this, but this is one particular tiling. So once again, what we have is an 8x8 board, and we have these 2x2 pieces, 2x1 pieces, which you can either lay flat like that, or you can turn them around. You can lay them vertically as well. Okay. And the question is, in how many ways can you cover the board completely using these 2x1 domino pieces? There's a nice variation of this, which is, I don't think if it's, I don't know if it's mentioned in the miniature, or I don't remember, but if you just had a 2x n board, so if you just had this portion that you're seeing of the blue region, and you ask yourself in how many ways can you tile. So this is more of a, think of it as a corridor or something. Um, so if you just had to tile a 2x n board using 2x1 tiles, then that has something to do with the Fibonacci number. And the reason I'm mentioning that is because we've seen Fibonacci way early in this series, so I thought that was a nice connection to make. The basic question you ask yourself is what happened at the end? Did you do one of these tilings like that, or did you do two of them like this? And those are two different ways in which the last bit of the corridor can be tiled. And then you apply a recursive formula for the number of ways in which any n-length corridor can be tiled. So basically, the number of tilings is captured is captured by the Fibonacci formula. It's interesting that, well, there is a closed form expression for the n by n chessboard as well, but it has. I actually didn't put it on the slides because it kind of looked even a little intimidating, and um, the claim was that you can get to it from the determinant, but I couldn't figure out how, so I didn't want to put it up while being completely clueless about from where it came. But it's something that involves the trigonometric functions. Looks totally crazy, doesn't look like something that should be a number, but apparently it is a count. So if you're curious, that's in the miniature, I think. But okay, moving along, I think this is what we want to count, the number of possible tilings, and we are going to try and relate a tiling to a structure in a graph. And the structure is what is called a matching. So let's just take a look at this. So we're going to take our board and transform it into a graph where the vertices are all the grid cells of the board, and two vertices are adjacent in the graph if the corresponding locations in the board can actually be covered by a 2x1 domino, meaning they're either horizontally or vertically adjacent next to each other. But notice that if they're diagonally close to each other, then that doesn't warrant an edge. So for instance, you have this location here and this location here captured by this vertex here and this vertex here. But in our graph, we don't have that edge because there's no 2 by 1 domino that can possibly cover just these two locations on the board, right? So you do need them to be either like this or like that. So you get this nice graph, which basically looks like a grid. And now if you think about a tiling, well, basically that's a collection of edges, practically by definition, because we said we'll throw in an edge exactly when those two locations can be covered by a domino. But if a collection of dominoes corresponds to a perfect tiling of the board, which means that no square is left out and no square is covered more than once, in other words, every square is covered exactly once, then those dominoes correspond to a collection of edges, which is called a matching. These edges are basically disjoint, and it turns out that because you're coming from a tiling, every vertex belongs to one of these edges. So a typical matching doesn't need to have the second property. So these matchings are actually special. They're called perfect matchings because they cover all the vertices that are around. So essentially, tilings correspond to perfect matching. So I should have qualified that a little bit further, but that's what we have. Okay. All right. So can you give me a +1 in the chat if the connection between tilings and its reformulation as a question about finding matchings in a graph, if that much is clear? Okay, wonderful. Thanks. So we basically boiled this down to counting matchings, and this is well, if you look at the graph associated with the chessboard, this graph is also what we call bipartite. I don't remember if we encountered bipartite graphs before, so let me just say that again. The notion of a bipartite graph would be that you can actually color the vertices of your graph in such a way that if two vertices have the same color, then they're not adjacent. So you can see here that there is this nice pattern, which is your standard chessboard pattern, I think, where all the vertices of one color basically are these kind of diagonal entries. So if you pick any two blue vertices, you'll see that they're not next to each other. If you pick any two yellow vertices, you'll see that they're not next to each other. So that's why the graph that's associated with a chessboard is bipartite. You can actually color it with just two colors in such a way that every edge in the graph has both of its endpoints colored with two different colors. Okay, so that's what a typical bipartite graph looks like. We usually draw it this way, where all the vertices of one color are on one side and all the vertices of the other color are on the other side. And the only reason these colors are kind of shaded or there's a gradient is just so that um, well, to be honest, I was just a bit lazy about labeling the vertices and using vertex labels to refer to them. But the reason I need to refer to them is because the next thing I want to talk about is the bipartite incidence or adjacency matrix. So I think some places call this just the incidence matrix, and if I remember correctly, the miniature calls it the bipartite adjacency matrix, but don't take my word on that. But anyway, this is going to be yet another matrix that we associate with a graph. So far, we've seen the adjacency matrix, we've seen the Laplacian, and this one is the incidence matrix. And again, I think there is a different, well, okay, maybe I should avoid using the word incidence matrix because incidences are basically relationships between vertices and edges. So the standard incidence matrix would basically have rows indexed by vertices and columns indexed by edges, so something like that. And you would have a 1 if the vertex in question is incident to the edge in question. So every column would just have two ones in it, representing the two endpoints. So this is not that graph. This graph is actually one that really this matrix, sorry, the definition of this matrix really relies on the fact that the incoming graph is bipartite. So the rows are indexed by all the vertices on one side of the bipartition, and the columns are indexed by all the vertices on the other side of the bipartition. And you can probably guess where the ones are. Does anybody want to propose the definition? When would the ijth entry be a 1? You're welcome to pattern match from the example. Again, let's hope that I haven't introduced typos here, but or also let me know if the question is too vague. Basically, I'm asking when would when would an entry like this be a one, for instance? What in the graph is yeah, exactly. So thanks, Sat. The idea is to take the row index and the column index, look at the corresponding vertices, and check if they're adjacent. So you're exactly right. You would have a one if there is an edge between the vertices that are being represented by the row and column indices. Okay, so that's excellent. Could you give me a +1 in the chat if the definition? Oh, okay, Jayati was yeah, maybe sorry, you probably overthought that a little bit. I should have said that it's really quite transparent. Yeah, great. Okay, so right, the ijth entry is a one if vertex I from the left side of the bipartition is adjacent to the jth vertex from the right side of the partition. That's how this matrix is defined, right? And let's just think about what the matchings correspond to in this matrix, because remember, we're interested in matchings because every tiling corresponds to a matching in a bipartite graph, right? So this is just the definition of the matrix on top there, if you prefer it in notation. In a case, is a bit of a giveaway, I'm afraid, but let's see. So here is a matching on the left, and the edges in the matching are highlighted on the right. Okay, so in some sense, does this remind you of something that we have seen yesterday when we were working with the Laplacian and we were working with a certain kind of a product definition of a determinant? So yeah, exactly. So Jayati is already pointing out that you have a unique row column situation. So from every row, so if you look at the matching edges, then, well, especially if it's a perfect matching, if it's a perfect matching, then I know that every row index is matched to, well, every vertex that's represented by these row indices are being matched to some vertex in the graph. So from every row, I know that I can go and pick out a one, which is basically the edge that's going out of this vertex, and it belongs to the matching. And wherever it lands on the other end is what I would pick up from the matrix. But notice also that you cannot have two vertices, you cannot have two things being highlighted from the same column, because when you look at it from the perspective of the blue vertices, it's also a matching for them. So every row is going to go and pick out pick out something from some column, but all the rows have to make sure that they're going to different columns, because if not, then you don't have a matching. The edges would no longer be disjoint. Right. So hopefully it's clear that what we have here essentially corresponds to a permutation of indices. It tells you any permutation of indices would sort of correspond to a matrix. So we did say that the answer to the question in the title of this miniature lies in determinants. So does anybody see already maybe what does this have to do with determinants? Can we say that the determinant of this bipartite adjacency matrix almost gives us the count of the number of matchings, except for like a stupid sign issue? Can somebody maybe confirm this intuition? If the determinant formula did not have the sign of the permutation, so remember that the determinant formula was this: we had a sum over. So we went over all these permutations, right? So these were permutations, and I'm going to call this Sn, which is all permutations of 1 to n. And then we did the product of the matrix entry. So in this case, this is going to be bi pi of pi, right? So this was, and then we had to multiply this with the sign of the permutation. Yesterday, on the previous miniature, we were quite happy about this sign term because it was helping us out. It was canceling things that we didn't want. But right now, I'm not very fond of the sign term. So let's just pretend for now that we're looking at this expression, which is not the determinant necessarily, but I've just thrown away the signs of the permutations. What do you think this is counting? In fact, I think I do have it on the next slide, hopefully. Yeah, so this is, we're not calling this the determinant because it's not, it's what's called the permanent. And that's basically the determinant sum, right? And the product has been written out explicitly, so you don't see the capital pi notation here. But this is essentially, so if I plugged in, sign term here, okay, I really cannot draw to save my life with the mouse. So if I plugged in the sign of pi here, then this would have been the determinant. But right now, that's, well, because that term is not there, this is the permanent. But can we say that the permanent meaningfully captures something about matchings, given the nature of the terms that are involved? So we do know that if you have a matching, then that naturally corresponds to a pi. What can we say about these entries? And also, there will be permutations that don't correspond to matching. So that there would be, for example, here, if we take the identity permutation, some of these edges are missing. They're not there. So the identity permutation is not a matching, but it is a permutation. It'll show up in the sum, but does it contribute to the sum? Yeah, maybe let's just answer that question. So does the identity permutation contribute anything to the sum? So the identity permutation corresponds to the product of these entries. So what's that? What's that product? Yeah, that's exactly a zero. So when you're looping over all possible permutations in this, in this sum here, and you encounter the identity permutation, then, well, you get the product of these terms, but there is a zero in there, so that's going to be zero. If you take any other permutation that does not correspond to a matching back in the graph, then notice that, well, I mean, you could try, you could say, well, let's try to match this guy with this guy, and feel free to extend this however you like. But because we're trying to match two things that are not adjacent, you're going to pick this out, and then you can do any permutation on top of this one. But because this is a non-edge, it's going to be a zero entry. And so that product is going to vanish. So my claim is that any permutation that does not correspond to a matching is going to not contribute anything to the sum, because there's going to be a zero entry in that product. So those terms are basically going to vanish from the sum. And on the other hand, if you are a permutation which does represent a matching, then each of these n terms in this product is going to be one, because you have all of those n edges, they're all one. So every matching contributes one to the sum. Okay, so fix a matching in the graph that naturally corresponds to a permutation, and hopefully that's clear. So for instance, this is highlighted on the slide. So you have a matching on the left that corresponds to this permutation that you see on the right. The permutation says 1 goes to 1, 2 goes to 4, 3 goes to 5, 4 goes to 2, and 5 goes to 3, something like this. right? So, so it's essentially one fixed point, and maybe it's just one long cycle on top of that, right? So anyway, this is a permutation that naturally corresponds to this matching. And when your sum is looping over all permutations and it hits this one in particular, it's going to, this particular permutation is going to contribute a +1. And conversely, if you have a permutation which contributes a +1 to the sum, then you look at the permutation and read it off as a collection of edges. You will find that those edges must form a matching, because first of all, they're all disjoint because it's coming from a permutation, so there are no overlaps. And those edges all exist in the graph because this was a permutation that contributed 1 to the sum. So all the entries in the matrix are +1, which means the corresponding edges must exist. So every matching, basically the terms that contribute a +1 in the sum are in one-to-one correspondence with all the matchings, all the perfect matchings in the graph, right? There could be smaller matchings, but they're all going to vanish. And yeah, so any permutation that doesn't correspond to a legal matching, those terms are going to basically be 0 and they vanish from the sum. So give me a +1 if this correspondence is clear, that you have, this sum basically picks up the number of perfect matchings in the graph. Does that make sense? Yeah, okay, all right. Thanks. So I'm going to move on. And yeah, so here, I think maybe I just wanted to work through the number of matchings in this graph. So okay, so I think switched the top and the bottom edges, and that's a different permutation. So you have the graph in the center, and notice that this particular graph just has 2 matchings, if I'm not mistaken. And the reason for that is that you have these 2 vertices with degree 1. So in a perfect matching, remember, you have to match everybody. And if some poor fellows only have one neighbor, then that is basically forced on them. So in any perfect matching, these 2 vertices, these 2 light vertices here will be matched to these 2 dark vertices up there. And that's basically a pattern you will see in any perfect matching. So we can forget about these guys. The rest of the graph basically looks like this. And this is, well, let's see, I think this is a 6 cycle. And from a 6 cycle, you basically have 2 choices of, you have to pick alternate edges. That's the only way to get a matching. And so the question is, do you pick, well, you can pick one set of alternating edges or its complement. So that's what gives you the 2 matchings that you see. So you can think of it as, did I pick the top edge or did I not? That's did I pick the top edge or did I pick the bottom edge? And I think those are the only two matchings in this graph. Now let's go back to the bipartite adjacency matrix and ask ourselves what's going on. We know that the permanent captures the number of perfect matchings. What about the determinant? Well, it turns out that in this case, we actually are lucky that even the determinant also happens to count the number of perfect matchings. And I don't know if I have it on the slides. No, I don't. Okay, the reason for that turns out to be that if you look at the 2 permutations which correspond to the 2 matchings that we just saw, they turn out to be, okay, maybe I just go back here. So where I actually have them. So if you think about what is the sign of this permutation, right? It turns out that the sign of this permutation is that's going to be a +1. And I think I casually said that this permutation is a fixed point plus 1 long cycle, but actually what it is it's 2 swaps, right? I think you have let's see if I have this right, because to be honest, I didn't fully think this through. I just computed the determinant of this matrix and it turned out to be 2. But let's see, we have 2 going to 4 and 4 going to 2. So that's 1 transposition. And we have 3 going to 5 and 5 going to 3. So that's another transposition. So that's the story for this matching. And I suspect that for the other one also, you'll have something similar because it's like so much symmetry. So, okay, I don't know if I had both of those. Oh, did I forget to change the matrix? I apparently forgot to change the matrix, although I changed the matching. But anyway, maybe you believe me on this. The two permutations that correspond to the two matchings in this example happen to be permutations whose signs are actually positive because they can be obtained with two swaps. And remember, we said that the sign was -1 raised to the number of transpositions that you can write the permutation as a product of, right? And in this case, you can write both of these permutations as a product of two transpositions. So luckily for us, the two permutations that we care about actually survive even after we throw in the full force of the determinant formula. So even after we append the -1 to the sign of pi, the two pi's that we care about, there are two permutations that correspond to matchings. For those two, the sign of pi happens to be 2. So those two terms survive, and even the determinant actually captures the count of the number of matchings. Now, you might be wondering what's all the fuss about, back saying, well, we have an expression that counts the number of matchings. It even has a nice name. It's apparently called the permanent. So why can't we just say that the number of matchings is counted by the permanent, just compute the permanent and be done with it? But the reason I'm coming back to the determinant and trying to see if the determinant can also be useful is because it turns out that from a computational perspective, the determinant is actually a much nicer quantity to work with. So it turns out that computing permanence is a really hard problem, whereas probably various ways of computing the determinant, and already that that's something that we can compute efficiently. It turns out somehow all of these cancellations probably, or well, maybe I shouldn't call it cancellation, but all of the the formulas look really, really similar, but they're really different from both a conceptual as well as from a computational sort of perspective, right? So the determinants are much more efficient. So if we wanted to count matchings quickly, we really don't want to be stuck with the permanent. It's an annoying thing from a computational perspective. And also the determinant seems tantalizingly close to what we wanted to count. It's just that there are these signed terms, and there's this we're always going to be living in the fear that what we care about, ends up getting canceled out, and we don't want that to happen. So the question we want to ask ourselves is the following: can we tweak this matrix a little bit so that, well, can we drop some signs? So can we change some of the +1s to -1s in the matrix so that they offset the sign issue that comes from the determinant formula? Okay, so I don't know if the question is clear, but let me just maybe illustrate with an example. So let's look at this. So this is back to the chessboard tiling example. So we're looking at one matching here. So maybe I don't know if it's important to point out the convention that I used for drawing out this matrix, but basically think of the vertices as being numbered from 1 to 16. Going from top to bottom, left to right. So the top left entry is 1, and the bottom right entry is a 16. And so these rows are basically the rows are basically all the red vertices. So this is the first red vertex, the second one, and so on. The columns are all the blue vertices in this order. So we have a matching here. This matching corresponds to the identity permutation. And now what I want to do is see if I can, let me show you a different matching. Here's this matching here. I've just sort of changed two of these lines that were parallel to the x-axis to now be parallel to the y-axis. So that corresponds to a slightly different permutation back in the matrix. And now notice that, well, this matrix, sorry, this permutation is basically one transposition, right? Because it's the transposition where we send, I think, 4 to 6 and 6 to 4, right? Everything else is a fixed point. So this permutation is a single transposition. It's one swap. So what is its sign? Its sign is going to be one, and so notice that this when we come to this permutation here, that term in the permanent will contribute a +1, but in the determinant will contribute -1. Is that clear? So give me a +1 if you can see that the determinant is dropping terms. So when we, right, thanks. So if we compute the determinant now, we get potentially an underestimate of the number of matchings, right? So for all we know, although this is not true for this example, for all we know, we had the starting matching and we had one more. And so our graph had just 2 matchings. One of them was associated with a permutation that had a positive sign. One of them was associated with a permutation that had a negative sign. And then in the determinant, those are going to collide. And we probably see that we misled into believing that the graph has no perfect matchings at all. So that's not so nice.
Yeah,
so what we want to do
there.
Sorry.
It's not -1 to the sign of my, it's just sign of my.
Oh, sorry. I think I wanted to say transpositions, I think. So this should have just been sign of pi. I don't know if there's a...
Yeah, and the sign of pi in this case will be -1.
Right. So...
which is what you don't want, I guess.
That is true. So I think so I kept going, okay, when I was trying to understand this, I kept going back and forth between sign and number of transpositions. So that explains where the typo came from. So the only thing is now, I don't know if I can hide this. Or the other thing is I could have changed that to transpositions. Okay, so all right, this is a floating sign of pi, but thanks, Vinay. I will fix this after the session. So yeah, so the sign of pi is -1 to the 1, which is the number of transpositions. In this case, this is a single swap. So like I said, we have the determinant dangerously dropping terms, which is not so nice. So my hope is that what we can do is, tweak some of these entries to maybe being -1 in the matrix. So now we're going to go and mess around with the matrix. And the hope is that if we flip some of these terms to -1, then this fellow here will emerge as not being +1, but -1. So even if the sign of pi is -1, this -1 will multiply with that -1 and go back to being a +1. Okay, so that's the goal of this so-called, I think what's now called the Castellian signing. I have no idea if I pronounced that right, but anyway, that's the question. And I think it's a very non-trivial question because different permutations are going to throw out different constraints, right? So when I look at this permutation, what I know is that I want to flip the sign of an odd number of ones among the ones that you see here, among the highlighted ones in my final signing. So again, just to back up a little bit, my goal is to change some of the +1s in this matrix to -1s according to basically the following constraints. So all of these permutations which correspond to matchings, I want these permutations to end up with an odd number of -1s if the permutation itself has negative sign. Okay, so if I'm in danger of losing this permutation in the determinant sum, then I want the content in the matrix to basically save me from this term getting dropped, right? So if an odd number of these terms are -1, then this product will be a -1, which will collide with the sign and flip it back to being a +1. But on the other hand, if I am at a nice permutation, which is basically the determinant is protecting this product because the sign of this permutation is +1, in that case, I only want an even number of these +1s to be flipped so that I don't fix what's not broken. I don't break what is already fixed, right? So this permutation is doing fine. So I don't want my messing around with the matrix to turn this into a -1, because then I'm dropping terms now that the determinant was actually not, the determinant was not messed up here. This term manifested as a nice +1 in the determinant sum. So when I change the entries of my matrix to save some of my other terms, I should not go and mess around with the terms that were doing fine. So for all of these terms, I only want an even number of ones to be flipped to -1s. So does the problem make sense? These are the constraints we are operating under. We want to know if there's a way of tweaking the signs of some of the +1s to -1s so that all the even permutations, or well, all the permutations whose sign was +1, among them only an even number of ones changed signs, and all the permutations that had a negative sign, among them an odd number of ones flipped signs. That's what we want to ensure. So this is the signing problem. Is this clear? This is all this is so that we can count matchings using determinants instead of permanents, and hopefully the procedure that we come up with for developing such a signing will also be efficient, because it's going to be ironic if we spend a lot of time coming up with the signing. That would negate the purpose of the efficiency gain that we get from going from permanents to determinants. Okay, so give me a +1 if the goal is clear. We want to change the matrix so that somehow the determinant behaves like the permanent of the original matrix. Okay, all right, perfect, thanks. All right, so this is okay. I wanted to try and do some blah blah and give some intuition here, but realize that I'm starting to run out of time, and so I'm going to skip. Whatever intuition I had was very vague anyway, so I don't think it's going to be very beneficial. But let me go ahead and introduce a little bit of terminology so that I can somehow get some of the main ideas across, and hopefully not keep you for too long. All right, so suppose you have a cycle in a bipartite graph. You're going to say, well, something that you can take as a fact if you don't know it already is that in a bipartite graph, all cycles have even length. This is not hard to check. So for instance, if you have a triangle, there's no way that you can partition it into two pieces such that all the edges go across, and you will get similarly stuck with any odd cycle. So bipartite graphs basically don't have odd cycles. So we're going to have whatever cycles we have even length, and let's say that this length is 2L. Now, if I suppose I have a signing of the matrix that also corresponds to a signing of G, because every one entry in the matrix corresponds to an edge in the graph G. So if I change a 1 to a -1, I think of that as a negative edge in the graph, right? So suppose we have a signing of either the matrix or the graph. I'm going to use that interchangeably. Basically, let's use n sub c to denote the number of negative edges on the cycle C. And we say that C has been properly signed if NC turns out to be congruent to L-1 mod 2. So this is, okay, let's see. All this means is, I think this is a nicer way to say it. If you have a cycle of length 4, 8, 12, and so on, so if it's a multiple of 4, then we are demanding that we have an odd number of negative edges. And if you have cycles whose lengths are, 6, 10, 14, basically you leave a remainder of 2 when you divide by 4, all of these cycle lengths have an even number of negative edges. This is a easier way to think about proper signing, because at least in my head, I can't keep track of L-1 mod 2, but odd even is kind of okay. So if your cycle length is a multiple of 4, I would want that there are an odd number of negative edges on it. And if the cycle length is such that it leaves a remainder of 2 when divided by 4, then I would want that it has an even number of negative edges on it. If this happens in any signing, then we say that this is a proper signing. It's a nice signing, and we'll see why in just a minute. This might sound very left field. This is the thing for which I was hoping to give some intuition with an example. But like I said, my own intuition is not very well formed, but I do believe that if you go and play around with the constraints that we just described, you'll probably start seeing the difference in behavior between these kinds of cycles. But again, that's so this feels a little out of the blue, but I'm just claiming that it's not as out of the blue as it seems. So it can probably be reverse engineered a little bit. Okay, so a cycle further is evenly placed if when you delete the cycle, you still get a graph with a perfect matching. Let's use terminology. And here is the first claim, which already feels pretty powerful. So the idea is that if you have that all evenly placed cycles are properly signed, meaning all the 4x cycles got an odd number of negative edges and all the 4x plus 2 cycles got an even number of negative edges, or the other way around. Let's see. No, it's the way I said it. Then if it's properly signed, then the signing actually achieves what we wanted to achieve, right? So this is the slightly tall claim, which I'm not going to prove. I anticipated not having time to get into this, but hopefully in the last few minutes, maybe I'll come back and try to give some intuition for what's going on here. Okay, so we will also restrict our attention to two connected graphs, because maybe I should have said this up front. This very lofty goal that we have for ourselves is not always doable, because counting perfect matchings is not easy for all graphs. But it turns out that if your graph is sufficiently nice, for instance, if it can be drawn on a plane without crossings and it's bipartite and it's two connected, which is to say that every edge belongs to a cycle, then it turns out that you can come up with a signing mechanism. And most of these assumptions can be dropped, but the planarity assumption is kind of crucial. You can't go a whole lot beyond planarity. You can, but not really a whole lot. So this is just the overall story. But here is our second lemma, which actually brings in the planar drawing aspect of the result. So suppose you have a graph that is planar, it's bipartite, and it's two connected. I have no idea why the premise is that it's both connected and two connected. I did sort of assume that two connected implies connected, but I could be wrong about that. But anyway, so just to be on the safe side, let's say that our graph is connected as well as two connected. Maybe the point is that the connected is with respect to vertex connectivity and the two connected is with respect to edge connectivity. It's just something that occurred to me now. But anyway, the whole lot of assumptions here. But basically to say that you have a nice planar graph, it's bipartite, it's very hard to disconnect it. You cannot, if you delete an edge, the graph will not fall apart because every edge belongs to a cycle. So if you look at the endpoints of that edge, you can still go from U to V, not via the edge now, but via the longer route on the cycle. So any path in your graph that previously used the edge UV can now just take this detour. So that's the intuition for the notion of two connectivity. It's basically saying that a single edge deletion is not going to destroy the connectivity of your graph. And if I'm right about this, the connectivity assumption is for vertices. It's the same thing, but we are saying that removing, okay, so normal connectivity just says that you can go from anywhere to begin with. So I think that's just what we have here. Okay, so that's the premise. But now what we are saying is that if you look at a planar drawing, a fixed planar drawing, and you have a signing which has the property that every boundary circle of every inner face. So again, these are, I think if you wanted to define these things properly, you probably need to invoke some proper like mathy terminology, but I'm just going to remain intuitive about this. So if you draw a graph on the plane, basically you get essentially a bunch of faces that, especially if it's a two connected graph, then every edge belongs to a cycle, and these these cycles more or less correspond to faces, where some of these cycles are large and they're going to contain other faces and so on. But let me just point out that the inner face is basically faces whose boundaries are cycles of the graph. The outer face is basically the infinite face, which sits. Okay, you look at, just the complete outer boundary of the planar graph in question, and whatever is outside of it is the outer face. So you're not talking about that, but you're talking about the boundary cycles of the inner faces. If these are properly signed, then you have then the signing does what you want. Okay, so we've gone from saying that on bipartite graphs, the evenly placed cycles are properly signed. We've gone from there to saying something about the structure of, instead of evenly placed cycles from before, now we're saying cycles that form the boundaries of a planar drawing. Those must be properly signed. And basically, it's probably not surprising that the proof of lemma B uses lemma A to get going. And apart from that, it also uses, to make certain parity arguments, it also uses Euler's formula for planar graphs. Okay, so there is a little bit of, there's like a few steps in this proof, but nothing, it's nothing crazy. It's almost along expected lines, but there's some clever parity arguments to be made. So once again, I'm not going to show you the proof of lemma B, but I'll try to convince you about why lemma B is useful. And I stated lemma A because it goes into the proof of lemma B, and that's the one for which maybe I will be able to tell you a little bit about how the proof goes. But with lemma B, I'm omitting it entirely because it does require a little bit of terminology to do with planar graphs, and there's a little bit of a careful counting argument involved, and I'm probably not going to have time for that. So anyway, lemma B, however, turns out to be the one that's actually useful. So remember, our chessboard was a planar graph. It has all these nice properties. It's two connected, and it's bipartite, and it's planar, and all of that. So, but you can show this, you can make this argument for any planar graph. So basically what we are going to do is start out with our planar graph, and we're going to successively remove an edge, which let's say, so notice that any edge in a planar graph is basically incident to two faces, right? In some sense, it connects two faces. So we are always going to pick an edge which connects the outer face to an inner face, and we're going to knock it out. Okay, and we're going to do this iteratively. So we're going to keep knocking out edges until we can't do this anymore. We're left with this kind of a skeleton. We end up with a planar graph where the only face is the outer face, okay, which means there are no cycles. So notice that as we do this process of pulling out edges, when we pluck out edges, of course, we affect the connectivity of the graph. So at this point, for example, at the very end, we have totally lost the two connectivity property. So that's fine. We don't want to maintain those properties as invariants. The graph will continue to remain bipartite and planar. Nothing changes about that. But let me say how we achieve the signing, making these big assumptions about, in particular, lemma B, right? So we ended up with this skeleton graph at the very end, which which has just this outer face, right? What we are going to do is sign these edges as we like. It doesn't really matter. So maybe give them all a +1 if you like. And now what we are going to do is slowly start putting back edges in the order that we saw them. And when we start putting back edges, well, this edge is going to basically complete a cycle of an inner face, which was the object of interest in lemma B. And lemma B basically gave us a sufficient condition for a valid signing. We said that, well, if if you look at these cycles and they're properly signed, then we are good. So the point is that what's going to happen is when you add back any one of these edges, they're going to basically complete one particular one particular interface, because the time at which they were plucked out, the other face that they belonged to was the outer face, right? So when you bring them back in, so imagine playing this video in reverse, right? Start bringing back these edges, and when you bring back the the edge that was taken away in the ith iteration, well, you have a signing so far, which we are going to claim maintains the premise of lemma B up to all the cycles that we have seen so far. And now you bring in this new edge, which is going to touch exactly one inner cycle. And these have all been signed in some fashion. I don't know. So I compute what the sign of this cycle is without this edge. It's not even a cycle until this point. But whatever sign I have, I can sort of reverse engineer what this edge needs to be for that signing to be valid. So for instance, here I have a cycle whose length is 1, 2, 3, 4, 5, and this is going to complete it to a 6th cycle. So I want a 6th cycle to have a, what did we say, an even number of negative edges, right? If I remember correctly. And I said that, well, let's start out by, taking all of these edges in the last graph and making them positive. So this guy should continue to remain positive because we don't want to introduce a single negative edge. But on the other hand, if these were all negative, I would probably make this negative as well. So the point is that however you have imposed a signing on the cycle that this fellow is about to join, that cycle has a certain sign right now, and we can always set the sign of this guy to be such that it's compatible with the demand of lemma B. This is a bit like the parity check bits that we used to add. You can always set the bit in such a way that something happens. Similarly, here you can always set the sign of this edge that is being added so that you get what you want. You achieve the sufficient condition to get a signing. So that's why it's kind of crucial that you're always picking an edge that separates the outer face from, that has on the one side an outer face or the outer face and an inner face on the other side. So that enables you to do this, because the problem is if you don't do it that way and you've removed, so for instance, if I remove this edge and I'm trying to put this one back, it's possible that this cycle demands that it should be signed positively, but this cycle demands that it should be signed negatively, and this poor edge is going to be very confused. But the outer face makes no demands, so that's why it's easy to, it's easy to patch things in when you do it in this particular way. So that's the kind of the high level idea of why lemma B is useful. And I think as an exercise, which I was hoping I'll get time to do, but I probably will not do it in real time. But I think it's a fun exercise to go back to the chessboard and apply a proof of this lemma. So I just cleaned out some of the edges till I had no inner faces left. And now you can slowly try to bring back. So I'm going to say that, let's say all of these edges so far are positive. Now I bring back this edge and I know that's a 4 cycle. So this better be a negative edge because a 4 cycle should have an odd number of negative edges. This guy completes this 4 cycle. And so this also better be a negative edge and so on. But now when I bring back this edge, let's say, now this better be hopefully clearly positive because this 4 cycle should have an odd number of negative edges. 2 of these edges are already positive and I have 1 negative edge already, so I should not mess around. So this should be positive. And so on. That's kind of the idea. So you'll see that you'll get 1 positive row and 2 negative rows. That's how this gets completed. And you can verify just as a sanity check that this is indeed a valid signing, that when you compute the determinant of this matrix with this signing, it matches with the permanent of the original matrix. So that's something that I did for small examples with some with a program. I didn't have the whatever to compute it manually, but that's just like a fun exercise to cross-check. The other thing I was wondering is, maybe for just the chessboard case, it would be nice if there was a standalone proof that was really doable without making, without swallowing everything that really went into the proof. So I think that's a fun exercise to think about as well. But let me just spend 2 minutes talking about the proof of lemma A, which is that, if cycles are properly signed. And this is very lazy. Sorry, this is directly from the miniature. But what do we want to say? We basically want to say something about, why cycles of length 4, 8, and so on, multiples of 4 should have an odd number of negative edges, and cycles of length, 4x plus 2 basically should have an even number of negative edges in them. And I just wanted to convey like a little bit of intuition for what's going on in this proof. I won't go through the whole thing systematically, but the idea is that we are essentially happy if if M and M prime. So take any two matchings in your graph, right? And look at the, so those two matchings basically correspond to permutations. Those permutations correspond to entries in your determinant sum, right? So if all my matchings have the same sign, I'm happy, because then I'm not losing information. So either I get +1, as many times as there are perfect matchings, or I get -1 as many times as there are perfect matchings. So either way, the determinant either will give me, a +100 or a -100 if there are 100 matchings, 100 perfect matchings. So I'm happy either way. So I just want to make sure that all my matchings end up getting the same sign. So to that end, I think the product that they look at is the product of the sign of M and M prime for any arbitrarily chosen pair of matchings. And a little bit of just, writing it out tells you that the thing to focus on is really the symmetric difference of the two matchings. So once you've gotten rid of the common edges, right? Because, hopefully that's reasonably clear that this product is really determined by what's going on the sign of the common edges. And if you look at any two matchings and you consider the symmetric difference, so you throw away everything that was exactly the same, the rest of it turns out to basically be a bunch of cycles, because every vertex will have degree 2. It'll have, if you look at it from the point of view of a vertex, it's going to have one of its, it's participating in two perfect matchings. So it's going to have degree 2, one edge from the first matching, one edge from the second matching. And this is true of every vertex that survives in the symmetric difference, right? So it's going to be a union of cycles, and these cycles are going to have different lengths in terms of it turns out that computationally, I mean, in the calculation, it's what do we want from the product of these two signs? We want it to be a +1, right? Because we want the sign of M and M prime to be exactly the same. So yeah, I mean, I think, I don't know if I want to get into this much more, because then I feel like I want to start writing more, and because I didn't put up enough stuff on the slides to carry on with the rest of the proof. But I did want to point out that the argument really has something to do with the structure of the graph, and the fact that when you look at, it's enough to focus on two matchings, and that when you look at two matchings, the thing of interest that emerges from the calculation is really the cycles that are formed by their symmetric difference. And from here, the rest of it is, I mean, I think it's a cute argument, but I don't know if I want to drag my feet about it right now or leave it. I think it's like all the gaps here. Lemma B, I'm not sure if that's, if you're already familiar with Euler's formula and how planar graphs generally are a little bit, then I think lemma B is also a nice exercise. But otherwise, I think it's okay to either take it as a given or just go and look it up. But otherwise, I think here this is basically just a matter of using the fact that these are. I think it's also important that these are evenly placed cycles, which is to say that the rest of the graph is a perfect matching and so on. And, just write this product out carefully. I wish I could pin down exactly where the difference between the multiples of 4 and the remainder 2's come in. I mean, I was convinced that they come in when I was looking at specific examples, because of the kinds of demands that are being made on, don't touch me or touch me. In terms of, some people are saying that let's keep the number of minus ones to be even here. Remember what we were saying earlier about, how the goals were. You wanted to flip for the permutations that were disappearing from. So this, by the way, is the this is the symmetric difference of the two matchings that we saw here. So this guy, so our constraints were of the form only flip an even number of ones here, but flip an odd number of ones here. So it turns out that if you just do like a lot of pedestrian case analysis, you will see that you should only flip an odd number of ones on these four things here. If you just combine what's going on, because if you flipped only an even number of ones here, it turns out that you will be in trouble with at least one of the permutations. So you really should be flipping an even number of ones here. However, and I don't think you can get this example on a chessboard, I'm not very sure, but another example I worked out by hand was when the symmetric difference had a 6 cycle instead of a 4 cycle. And there it turns out that if you just look at what the constraints are telling you, where should you be flipping? So one of the matchings will tell you flip an even number of ones or whatever. The other guy tells you flip an odd number of ones here. Or whatever these two matchings tell you, once you sit down and actually impose those combinations of constraints, it turns out that it boils down to on the 6 cycle, it boils down to only flip an even number of ones. So this is something that you can, this is what I was saying earlier, that the difference between what's going on with the cycles whose lengths are multiples of 4 and those which are not, it seems like it's not clear where it's coming from, but it does fall out from just observing the constraints that are naturally imposed by the definition of the signing. So there is actually, I mean, although I don't think I communicated it at all, but I'm just going to say in a very black boxy way that in the calculation, you will eventually encounter some intuition if you do go through with it. But I think this idea was kind of really cool, that you basically tear off one edge at a time, connecting the outer face to the rest of the graph until you only are left with the outer face. Do whatever you want there and just carefully bring everything back using the power of lemma B. And then you have a signing. And of course, this means that we do have lemma B as a black box, but considering the time constraints that we are operating under, I think I'm going to basically leave it at that. So the key takeaways are that, well, tilings can be seen as matchings. Matchings can be seen as permanent, and in some special cases, the permanent can also be seen as a determinant of an appropriately modified matrix. So those would be the three main takeaways, with a lot of little gaps in the proofs, which I hope you'll have fun filling out in your own time. So yeah, all right. So I think I'll stop here, but questions or comments would be very welcome. Okay, so did the main high-level takeaways sort of make sense? Seeing tilings as matchings as the permanent, hopefully up to there it's kind of okay. Modifying your graph so that the permanent also becomes a determinant of a signed graph. I think that's the part where like all the detail lies. I think just maybe if you go away from here knowing that this can actually be done for bipartite two connected planar graphs, and you have some sense of the algorithm that does it. Algorithmically, it's basically this, like, so hopefully you can see that the procedure is efficient, but the fact that it works does require a few more arguments. So yeah. Vinay, did you have any closing comments here? Thanks, Jerry. I'm glad the broad picture was kind of okay. Yeah.
Yes, I have mixed feelings about this. I mean, I used to know this once upon a time quite well, but I can't, I mean, it's been more than 27 years or something. Yeah, a really long time back. So No, at the level of a broad picture, I think probably that came through, but I don't think it gives any sense for why this actually worked out. So in general, as you mentioned, you cannot take a permanent of a matrix and convert that into determinant. I mean, that's a very unlikely event.
Right.
But you can do it in some special cases. And this seems to be one of the special cases. But some intuition as to what allows it in the case of, is it bipartite planar graphs in some sense? Or is any planar graph can be.
Yeah. So I think,
So this.
yeah. So I think just for the record, I think bipartiteness is not the serious. I mean, bipartiteness is not what's helping us a lot here. I think,
Planar graph, right?
yeah, it's mainly planarity. It can be extended, I think, to all planar graphs. And the graphs for which these signings exist are apparently called Pfaffians. I don't know if I'm pronouncing that right, but it has a P, which I assume is silent.
Yeah, it is a Pfaffian. And
Right.
Meena and I have a paper on Pfaffians.
Okay,
So
right.
that's, so actually,
Um,
it's the only known polynomial time algorithm for Pfaffians. The other methods of doing Pfaffian is to compute a determinant of a slightly larger matrix, and then you take some square root and you get the Pfaffians.
Right.
Yeah. So I think, so we gave, I don't know if it's only now, it's 20 years. So it probably was the first to do it. Yeah.
Okay.
Yeah, but I've forgotten the material at this point. So I was hoping it'll jog my memory, but it hasn't. Okay.
Right. Okay. Yeah. No, fair enough. I think I did. I mean, yeah, I mean, part of it is also, yeah, I don't know if I have to think about if I can manage the time that I have better, but I think so with the heart of it is in these two, in the two technical lemmas. And I think with lemma B is, I don't think the proof is necessarily hard, but it is a bit of it has a few steps, and it does invoke, I think, a bunch of parity arguments, and part of it, okay, the planarity is getting exploited indirectly in the fact Euler's formula and how the number of faces are related.
Yeah, so maybe this is already a special case of the more general theorem that Castellian probably had.
Right.
Yeah, so maybe this is you're doing planar bipartite, right? So maybe it's a simpler case. Correct. But I do remember, I think Vijay Vajirani had I think a paper which showed that, I mean, if you look at planar graphs, either they have two forbidden minors, right? Either K5 or K3, 3.
Right.
So I think he was able to drop one of them and then show that you can still get these
something. Okay.
Convert permanent to determinant even if one of them were. Yeah.
Oh, that's fascinating. Okay, I should go and look that up then. Yeah, so I think that's along the lines of generalizing. I was also thinking along the lines of specializing, not to get anything new, but just to see if there's an alternate proof which is maybe significantly simpler just for the grid. So, and of course, in planar graphs, is I think this general sense that if you understand the grid, then you can probably develop some intuition anyway. So I did very, very briefly try if the detail with the Euler formula, etc., can be bypassed, and if a standalone proof can be worked out just for the chessboard. And then my initial grand plan was to just keep this whole discourse just about the chessboard. But I wasn't able to come up with a simplified proof for that special case. So that's something that I hope to, because in the miniature, he claims that this thing about color the alternate rows, color the edges on the alternate rows or columns negative and you're done. He says that the signing is very simple and it's here. And the proof that it works is by the following lemmas. So it's not, I was hoping that proof may be independently easy to see or come up with, but without getting into this business of whatever is being said in lemmas A and B, it wasn't clear, at least to me. But then, to be honest, I really haven't spent time trying to crunch this at all. So, but to some extent, I think I can reassure anybody who's interested that lemmas A and B are imminently verifiable. Like, I think it's just a matter of, I don't know if I should call it routine, but I think if you look at it, for example, the presentation in the miniature is it's a nice exposition, and it's followable. So if anybody wants to go back and do that just to complete this proof, then then please do. I'm debating about whether I should spend another session just completing the details, but then that also pushes back our global schedule a little bit. So I'm just trying to figure out these trade-offs, and I think when that I've been doing these calculations, so let's see. But for now, my plan is to maybe call
sure,
on this particular one. And yeah, so the missing details are the planarity is being leveraged. All the other assumptions can more or less be dropped. So the bipartiteness, even the two connectivity and all of that. But the two connectivity made life easier for us because we could just do this thing about this process, I think. And also the proof of lemma B, I think, was just simpler because we made this two connectivity assumption. So I think that's what Matuszek chose to do to make the proof simpler. And I think a nice homework exercise for us is to make it even simpler and see if there's a standalone proof for the chessboard, which can be worked out from first principles. So yeah, that's an invitation to anyone who wants to think about it. Yeah. Okay. All right then.
All right. Thanks. Yeah.
I'll look up your paper on Pfaffians as well. So yeah. All right. Thanks so much. Yeah. And perhaps we stop here.
Yeah. Don't ask any questions about it because I have absolutely no memory of it.
All right, but we'll go look it up anyway. Yeah. All right. Thanks so much. And
thanks. Yeah.
Good night, everybody. Thanks for joining. See you back tomorrow. Bye-bye.